Today we will continue our discussion on advanced cache optimization techniques. Last lecture we have seen some of the optimization techniques that are used to reduce average memory access time. To continue our discussion, our basic assumption was like average memory access time is dependent on hit time, miss rate and miss penalty. Now any of these three parameters, let us say it is hit time, miss rate or miss penalty, a variation in any of these three parameters is going to affect your average memory access time. The next technique we are going to work on is merging write buffer. We have seen that there are two categories of caches depending on how write is updated to next level of memory. We have write back caches and write through caches. Write back caches are those in which main memory will be updated only if a cache memory block is being evicted out. All writing happens strictly in the cache memory such that all further reads will be serviced from cache memory itself. So, there is no need for cache memory and main memory to be coherent. But when you flush out a block, you see whether the block is modified or not. If the block is modified, then the writing back happens. Another category of cache is called write through cache. Any writing that happens on cache memory is being updated in the main memory also. But processor need not wait for the entire write to get over. A special storage structure called a write buffer is used in this context. The idea of write buffer is when processor wants some updation to happen in the next level of memory, it writes in cache, at the same time it writes in the write buffer also. Write buffer will write it into the main memory or the next level of memory, at the same time processor is continuing. So, by this processor is not stalled, the writing happens in background and in the foreground processor is working. The optimization that we are going to discuss now is about write buffer merging. Write buffer merging to reduce miss penalty. So, write buffer is a structure where processor will continue without waiting for the writes to get over. So, when you perform a store or a write on a block that is already pending in the write buffer, update the write buffer. That is the idea. So, any write that you do, an entry is made into the write buffer for that particular block. There is a change that happened in one of the word is modified and the entire block is kept in the write buffer. So, in the near future, let us say one more write happens into the same block, that also will find a new entry in the write buffer. But the optimization of write buffer merging means when you put a new field or a new entry into the write buffer, you search inside the write buffer to see whether a same block has already an entry or not. If so, you merge the write buffer entry. This will reduce the stalls due to full write buffer. The policy is any write that happens, an entry is done in the write buffer also. Let us say a write buffer can accommodate only 4 such writes. Once 4 writes are there and write buffer has 4 valid entries, then processor is stalled because of the fact that any more write, there is no more space in the write buffer. So, when write buffer completes one write in the main memory, then one of the entries is freed. So, when you have multiple writes to the same block in an unoptimized write buffer, all these writes will occupy one block or one entry each in the write buffer. The idea of write buffer optimization is to make sure that pending write buffer concepts are already been improved. So, if the write buffer is full, writes incur, a processor stalls. So, consider this case, you can see that there were 4 write that happened into addresses 100, 108, 116 and 124. So, to memory location 100, 108, 116 and 124 were returned, let us say in subsequent clock cycles. Since all these are writes, write buffer is actually taking 1 entry each. So, 4 entries in the write buffer are already done. Now, by this time the write buffer is full. The optimization means write buffer controller should have an intelligence such that it has to understand that 100, 108, 116 and 124, they are part of the same block. This is what is known as write buffer merging. So, when you have write buffer merging, it is going to help us. That means the sequential addresses can be placed in one entry. So, you will get more amount of space. Moving on to the next optimization, which is called compiler optimization. This is a place where little bit of extra information, if a compiler can provide to the architecture, then we can improve the performance. Average memory access time can be improved. So, compiler optimization to reduce miss rate. The first one is known as loop interchange. So, whenever we have loops, especially in the case of nested loops, sometimes swapping of the indexes of the loops will give you better memory access because of the spatial locality that is available. In this mechanism, what we are trying to do is maximize the use of data in the cache before it is discarded. Let us say in an application, especially when you work with loop, you are going to bring a block of data. In the block, few of the sub elements may be accessed, and then you are going to bring the next block. So, once you bring newer blocks, the older blocks has to be thrown out. You may need these older blocks again because your algorithm is written in such a way that you are not going to make use of the entire data that is available inside a block. You bring a block, only partially use the data that is available. So, in this case, if the compiler can reorganize its code in such a way that the available spatial locality should be fully utilized. Consider a loop like this. For j is equal to 0, that is varying, and then you have an I loop, and then you have an array that is getting updated. X of ij is equal to 2 into x of ij. So, whatever is the number that is stored in x of ij, I have to double them. So, the idea is you have an array, take an element, multiply it with 2, store it back into the array. Now, the peculiarity of this loop is you can see that the second index of the array is varied by the outer loop. Since in arrays are stored in raw major format, such a kind of an access is going to create more number of misses. Rather than that, if the compiler could generate a code something like this, it is actually memory friendly. What we do is only interchanging the I and j loops, the body remains same. So, whatever you have brought, they are in raw major format, and the access is also in raw major format. So, this technique is called as loop interchange, where we are going to reduce the number of misses significantly. Moving into one more type of compiler optimization is known as blocking. Instead of accessing entire rows or columns, what you do is subdivide it into smaller matrix of smaller size. This requires more access, but it improves the locality of access. So, consider the case that you are going to perform a matrix multiplication, our standard matrix multiplication loop with I, j and k loops. Let us say this is the value that you are going to get in x by multiplying the value of y and z. You can see that those array elements which are light, they are not touched, they are not yet worked out. Light color means, especially these sections, they are older access, and dark color means these are all newer access or recent access. Our conventional matrix multiplication code, when you work, then you could see that whatever elements you have brought in, they are not completely utilized. This code can be rearranged in such a way that this is a modified version of this code done with the help of blocking technique, where whatever elements of y and z already brought, they have been completely utilized such that in future we do not want them. So, we may not be able to get exactly the value of x immediately, multiple times you have to do, but surely this blocking technique is going to reduce the memory access time by effectively reducing the miss rate. Next optimization is known as hardware prefetching. The idea of prefetching means a block is brought to the cache memory before it is requested. When a block is requested, we call it as a demanded block. Then the appropriate block is being brought into cache memory upon demand. Can we have some mechanisms by which we could predict what is going to be the future demands and then bring those blocks a priori such that whenever they are really needed, they are always available in the cache? The technique of bringing a block before it is demanded is known as prefetching. So, when you do prefetching, then we are trying to improve the hits. You are trying to reduce miss rate as well as miss penalty. So, prefetch items before processor request for them. What you do here? You fetch more blocks on a miss. So, whenever there is a miss, you bring the demanded block as well as a prefetch block. So, how will you find out what is going to be a prefetch block? We use prefetch engine or prefetch controller, which looks into what is the pattern of memory access, such that if there is an access to location L, we should be able to find out L plus delta L, what is going to be the next location, and prefetch that. And the most commonly used method for prefetching is sequential prefetch. That means if you bring block L, then L plus 1 is also brought. Requested block is kept in iCache, and the prefetch block is kept in something known as stream buffer. So, stream buffer is an extra storage, and this extra storage is going to keep the prefetch block. So, whenever you get an address, you search in the cache memory, in the instruction cache. If it is not available, then look into the stream buffer. So, this can be considered as an extended version of your cache, where you are keeping few more blocks of data in the cache memory. So, if a missed block is in stream buffer, then it is not like a cache miss. You are effectively having a cache miss, but with of a lower penalty. So, what we have in the prefetcher is like processing engine is going to have a history recorder, and then there is the aggressiveness module which will find it out how much you have to prefetch, from where to prefetch, and how many blocks you have to prefetch, and based upon that request is given. Prefetch request is given to memory, and the prefetch data is brought back. So, prefetching is a technique by which a block is being brought to cache memory in advance, such that when it is really demanded, that you will be having its presence in the L1 cache or its near vicinity. So, we call that extra structure which will store the prefetch data is known as a stream buffer. We have seen that we could, if you enable prefetching, this is some of the benchmarks in spec 2000 suite, you could see that if you enable prefetching, the performance is improved across various benchmarks. We can see that some of the applications like eQuake, we are able to get performance close to 1.9, whereas some of the applications like FAM3D, we are getting only up to 1.18 times. Even though they all are improving performance, certain applications will benefit greatly from prefetching. These are characteristics of the memory footprint. Some applications are prefetch friendly, whereas some of them may not be prefetch friendly. What we discussed just now is a hardware prefetching. The other one we are going to discuss is prefetching with the help of compiler. So, compiler is going to introduce certain instructions which will tell that these instructions are going to be needed, or these memory addresses are needed in the near future. So, that should be prefetched. So, certain prefetch instructions are added in the compiler code. So, prefetching will give performance only if processor read from caches and execute while prefetching is in progress. So, we can have two types of prefetching. One is called the register prefetch, where you load say data into register. The other one is called cache prefetch, where you load the data into cache. This is a costly affair, the register prefetch, because you have very few registers. When you prefetch, an existing data that is kept in the register has to be flushed out. In the case of cache prefetch, we have to make sure that the cache is not polluted. So, using loop unrolling and scheduling for prefetch data of adjacent iterations. Let us say you are going to work on an iteration of loop. When you work with the first iteration, you know that the second iteration will also be visited. For example, you work on a for loop which ranges from 1 to 10. When you work on iteration 1, and looking at the pattern, the compiler should be able to tell that this particular code is going to iterate from 1 to 10. So, the data which is required for second iteration is prefetched when the first iteration is in progress. Similarly, the data for the nth iteration is going to be prefetched when n minus 1th iteration is in progress. In that way, compiler is going to help the hardware by prefetching data and instructions that is needed in the near future. So, we have learned few of the advanced cache optimization techniques. The first one we learned today was about write buffer merging. Whenever a write merging occurs or whenever there is a write occurs, we look into the write buffer to see whether there is an entry for the same block in the past which is not yet completely written. In those cases, just merge the entries to form one block. And then we have learned about hardware prefetching. We have learned about compiler optimizations, wherein loop interchange and blocking techniques are being applied in order to get performance. And the last one is compiler assisted prefetching. So, with this we complete our basic optimizations and advanced optimizations in cache memory. We will now work out few of the problems related to cache memory which will give you a better grip on the topics. Thank you.